All right, for our last video, we're going to talk about what it means to remove core electrons. So far we've been focusing our energy on trends in ionization energies for outside electrons, for the valence electrons. But core electrons are exceedingly hard to remove. Okay, so let's take a look at an example, our good old friend sodium. Its electron configuration, if you don't have it memorized by now, neon 3s1. Okay, to take away that one electron in the 3s orbital, i.e. 1, so the first electron ionization energy, is roughly 496 kilojoules per mole. Right, so that's to remove one electron. Okay, if we were dealing with something like aluminum that loses 3, we would have IE1, IE2, IE3. Okay, so to remove one electron from sodium, 496 kilojoules. That brings us down to the core electrons, right? So in order to pull off one of those core electrons from the neon part of things, IE2, that ionization energy is 4,600 kilojoules per mole. Right? That's what it takes to pry off one core electron. Right? Nearly 1,000 times more energy. Right? It's really, really tough to pull off a core electron. And so let's take a look at a slightly larger example. So I mentioned aluminum. And aluminum is a good example because we have multiple electrons to pull off before we get to the core. So let's look at how that shapes up. All right, so IE1, to pull off the first electron, 580 kilojoules per mole. Right, I'm going to omit the kilojoules per mole for the sake of simplicity, but it's all the same unit. So IE2, to go from aluminum plus to aluminum 2 plus, 1,800 kilojoules per mole. IE3, to go to aluminum 3 plus, 2745 kilojoules per mole. All right, so this would be aluminum plus, this would be aluminum 2 plus, aluminum 3 plus. So here at aluminum plus we have neon 3s2, nothing in the P. Here we have neon 3s1. Here we have just neon, so we're down to the core when we're at aluminum 3 plus. Now to pull off one more electron, I have to dig into the core electrons, and we go from 2745 all the way up to 11,600 kilojoules per mole. Not likely to pull that off. Certainly not in nature. We could probably do it in the laboratory, right? But in nature, a energy cost of 11,000 kilojoules per mole to put in, not very likely. So aluminum 4 plus doesn't likely exist in nature. It's just too much of an energy tax to get there. Okay, so looking at these ionization energies that we have here, 580, 1800, 2745, and then jumping up suddenly to 11,000, you can see that this would be reasonable. Okay, and then we have a huge jump here, right? Telling us that when we've made that kind of an energy leap, we're digging into core electrons. So just being given ionization energies, you should be able to surmise where something is on the periodic table based on what type of ion it makes, how many ionization energies it's likely to have before it takes off a core electron. Okay, so I did lie, and we do have one more topic to discuss, and that is the concept of paramagnetic versus diamagnetic. Let's switch up colors here. Okay, now the easiest way to remember this is that para is unpaired electrons. Para is unpaired. Okay? Unpaired electrons are magnetic. Okay? In other words, are attracted to magnetic fields. All right, so let's take a look at carbon, for example. All right, so carbon's electron situation, and these are most easily solved by drawing the boxes. So I've got my 1s, my 2s, and my 2p. All right, so I've got two unpaired electrons. Means that it's paramagnetic. Attracted to magnetic fields. All right, unpaired electrons are attracted to magnetic fields. These two guys sitting all by themselves in these boxes with no partners in those boxes means that they are unpaired. All right, let's look at another example. Let's look at zinc. All right, has an electron configuration argon 4s2 3d10. All right, so let's draw the boxes for that. It's really helpful to draw those boxes. So here's our 4s. And our 3d. All right, so I've got, let's switch to the red. 2 in my 4s, and then I've got 10 in my 3d. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? All paired. No singles. Right? All paired means diamagnetic. Okay? In other words, not attracted to magnetic fields. Right? So a piece of zinc will not be attracted to a magnet, where a piece of carbon will be weakly attracted to a magnet. Right? Slightly magnetic. Right? Let's look at one more example. Let's look at iron. We all know that iron is magnetic. Anybody that's played with a magnet as a kid knows that things that have iron in them are magnetic. So iron has a 3d6 for its shell. Sorry, words just failed me. So if I look at that d6, right, we have 1, 2, 3, 4, 5, 6. That means that we've got 4 unpaired. So paramagnetic. More so than carbon. The more unpaired electrons you have, the more magnetic that element is. Right? So 4 unpaired electrons versus 3. So you can imagine that something with 5 unpaired electrons would be even more magnetic than iron, more attracted to magnetic fields. Right, that does officially do it for my Chapter 8 material. I hope you've enjoyed the ride, and we'll see you again for Chapter 9.